still on that 1-800. Hit me up for a good time. My shit buns till it push me out of line. You can't spell my name without the dollar sign. Rainbow money, take whatever. Yes, I'm colorblind.
There we go. That was epic,
Energy.
man. I got to do this
That's what
much
we
more
want.
often. Walk-in song is the way to go. What's up, everyone? I'm Eugene.
And I'm Caarn.
It's good to be here with y'all. I wanted this slide to come up earlier because I wanted to hear people's reaction in the room because it's one of two. It's either like, oh, cool, or, yeah, you know.
You know?
But,
Yeah.
so anyways, for those, I will not repeat that. For those who haven't met us, I'm Eugene. I am a self-taught software engineer. I currently work as a CTO of a tiny consulting company here in Stavanger. I am a dog kind of person. I wanted to put a bunch of pictures of my dog up on the screen. I was told not to, unfortunately. I'm also a retro gamer, used to be called a gamer. And one day I just got old and then they're like, oh, you're into retro games. No, I'm just into games. But it is what it is. So that's me.
And I'm Caarn. I am also self-taught. I work as a software engineer at Capgemini. And I am definitely a cycling enjoyer. All different shapes and sizes, clearly. And then free beer enthusiast. So if
Aren't
you
we
want
all?
to supply, I'm here.
You got the demand. However, who are we not, Caarn? Are we physicists?
No.
No. Are we quantum scientists? I don't even know if that's a thing.
Maybe?
But
No.
we're definitely not because we don't even know if that's a thing.
Yeah, no.
We are, according to ChatGPT, I asked it, and it said that we're just two guys with Wi-Fi and questionable life choices. So you know what? That was a good line.
Accurate.
I do appreciate that. But so you're wondering, okay, if you don't know this, then why are you doing this? About 6 months ago, we were sitting at work. At that time, we used to work at the same place. And then we saw the call for papers for this conference. I had just watched the talk on quantum computing, and I think I understood one thing. And I was like, oh, hell yeah, this stuff easy.
We were high on sugar and just energized.
So I said to Caarn, you want to do this? He's like, let's do this. So really, I think we can quote the old developer mantra of we didn't do it because it was easy, but because we thought it would be easy, right? At the time, it's like, how complicated can it be? It's got the word computing in it. But it also has the word quantum in it, which turns out is much, much more complex. So, with that out of the way, what the hell is quantum computing? Let's get into it, but before we do, I have a disclaimer. You're going to see quite a bit of this up on screen. Not a lot of it, but some of it. This subject is it's way too big. There's so many things that we just don't have the time to get into, or that we just simply still don't fully understand. So you're going to see certain things that you're just going to have to take our word for it, that it works in that specific way. If you don't agree, go research it. I think there will be a HelloStavanger next year. Make a rebuttal talk. Be like, why those guys were wrong. But that's in a year from now. So for now, if you see this come up, just trust us. That's what our research seemed to indicate. Another disclaimer, we're not going to talk so much about quantum mechanics. We're going to talk about quantum computing. So it's kind of like if we were going to talk about classical computing, we don't really talk about electrical engineering, right? The two concepts are very closely related, and one really builds on the other. But there's not so much need to talk about the specifics of the mechanics. If you've been living under a rock and have absolutely no idea what quantum is in general, we can just say, back in the 1900s, Max Planck, Albert Einstein. Is this too boring for you, sir?
Carry on.
Nice,
Nothing to see here.
nice spread there too, buddy.
Oh.
Let me have you. There we go.
Sorry about that.
They saw that particles at the atomic and subatomic levels behave differently from things in the larger than atomic levels, right? Things did not follow the rules of conventional classical physics. They behave differently. Some decades later, someone figured that, hey, we can use those properties, we can use those odd behaviors to perform calculations, to do math on them. And that is where where quantum computing got started. So we're going to talk about the second concept here. So having said that, who has heard about quantum computing before? Read an article, heard that it exists, is scared that it's going to destroy all the banking in the world and so on. Okay, I see, I think most hands. Who hasn't heard about classical computing?
Quantum.
Sorry, that was a trick question. Quantum computing. All right, I did not see any hands. So here's a misconception that I had when we started looking into this. Also, by the way, in the back, the clock still says 45, so I'm just going to keep talking. I don't think it started. I do have a timer here, but just so you know. Give a shout if we run out of time. The misconception I had was that once quantum computers became mainstream, we were going to be able to do infinite amounts of computing in basically no time. Quantum computers were going to be just this completely exponential change on what computers do. They were going to be able to do anything that takes a really long time now with classical computers in very little time. So therefore, this was, again, going to destroy cryptography, was going to ruin all international secure communications, and so on and so forth.
X's.
Yes. Have you heard this before?
Yes.
You've heard it before. Had you heard this before? And is that maybe the concept you had coming into this? No, just me. Okay, so I guess I'm the idiot. But it is not like this. However, it's not entirely wrong either. There is parallelism. There is not infinite power.
Unlimited power. Let's go.
I have my color commentator on the side here. Oh, we're not allowed to say that anymore? All right, I got my hype man
I'm okay
here,
with it. It's fine.
I got my whole crew here. This is beautiful. So, let's go into, finally, how it is that quantum computers work. First of all, we got to understand the concept of bits versus qubits. A bit, depending on who you ask, is a different thing. You ask a computer scientist, it's a 1 or a 0. You ask an electrical engineer, it's maybe a capacitor that has a charge versus one that doesn't have a charge. You ask a comedian, it's a joke, right?
These bits. Sorry.
I will not comment on that. We might not make it to 45 minutes. But yeah, classical computers, they perform calculations on ones and zeros, right? And even though they are very fast, they perform these calculations sequentially. They try one, then they try the other, then and so on, right? Quantum computers work with a concept called qubits, which is really just quantum bits. These qubits also give answers of 1 and 0, but the crazy thing about qubits, and this is where it starts to get wild, right? The crazy thing about qubits is that they can be in both states, both 1 and 0, at the same time. A regular bit is either a 1 or it's a 0. It can't be both. Qubits are both at the same time. And to illustrate this, I tried to bring a coin, but I didn't have any at home. I haven't seen a Norwegian coin in maybe 10 years. Does anyone have a coin? Literally not a single hand went up because we don't use physical money in this country, right? But imagine you are in a different country and you have a coin. There we go. For example, they use coins, right? They only use coins, if anything. Think about this coin, and now you put it on a table and you spin it. This coin starts spinning. When you're looking at the coin spinning like that, which side are you looking at? Are you looking at the front or the back? Now, you might be a smartass and say, well, you're looking at one and the other really fast. But just for the concept of illustrating the qubit, when a qubit is in transit, let's say, when it's being worked with by the quantum computer, it's kind of representing both states at the same time. If I said to you, Glenn, all right, let's bet on something, and if it's heads or tails, and I gave you this, and I say I win, you would say, no, that's bullshit. Exactly. Because right now, it's both heads and tails, right? We need to actually do something to this qubit to be able to get an answer. Is it heads or is it tails? Now, which answer will it be? If it's a regular coin, it can be either. We can say it's about 50-50 probability, right? But keep in mind that concept of probability and of seeing a bunch of different states at the same time, because that will come in handy later. These qubits have another crazy property. This is some black magic, which is called entanglement. Entanglement means that you can take 2 or multiple qubits, as my assistant here is helpfully demonstrating, and you can entangle these qubits, which means that you kind of sync them to each other. Once these qubits are synced to each other, and this is true of just quantum particles in general, but in this case, we're talking qubits. Once they are synced to each other, you could have them on opposite sides of the universe. And the state of one will affect the state of the other. These two are now synced regardless of where they are physically. It's mind-blowing. Isn't it?
Mind-blowing.
So with that property, you can then take a bunch of qubits, you can entangle them, and you can perform those calculations where you're doing stuff both on the 1 and on the 0, let's say, at the same time, which is pretty crazy. So once you get those two things together, you get that superposition, and you get that entanglement. You remember that scene, Caarn, in, I think it was the Avengers. I'm saying you remember as if I watched it. I didn't watch it. But I've seen the scene specifically where he says, Dr. Strange says, like, I've looked at all 194 million futures, and I found the right one, right? I'm thinking he did it at a quantum level. He went and looked at all 194 at the same time, right? And just found the one that was the one where they were able to win that battle or do whatever they were going to do.
Parallelism.
Parallelism,
This guy.
right?
Yeah.
So then you might say, okay, but you did just tell us that these computers can't do all these operations at the same time. Yes, they can, but there are limitations. But they are able to do large amounts of operations at once. And they are able to give us exponential growth on problem solving, computer problem solving, but it has to be on a very specific type of problem. Now, Caarn, are you familiar with NP problems?
No.
Now, you might think
No.
that NP stands for no problemo, but it's all problemo. These
problemo.
NP stands for non-deterministic polynomial time. If you are a computer science graduate, you probably learned about this in school. These are problems where you are able to verify a solution very quickly in polynomial time. Means very quickly. However, finding this solution, finding a solution, takes exponential time. It takes a really long time. So once you have a solution, you can check it. Is it the right solution? Yes, no, real quick. But finding that solution is what takes a really long time. What are examples of NP problems? For example, Sudoku. If you think of a Sudoku board game,
I'm familiar.
you're familiar. You like numbers, right?
Yeah.
You know,
sometimes.
you know up to at least 9, right? That's all you need to play Sudoku.
Really?
Right.
Yeah.
If you think of Sudoku, once you have an answer, you can quickly check to see if it's the correct answer. But getting to the answer, that's the game, right? That's the difficult part, sitting there thinking, adding, subtracting. Once you have it, though, you can check it.
You should say. Yeah.
Do you know about the problem of coloring a map, where you have a map and maybe 4 colors you're allowed to use, and you need to color each area in a different color so that no 2 contiguous areas share the same color?
Like gerrymandering.
Like gerrymandering. Once you have a solution, you can quickly look at it and say, like, yes, I'm not going to comment.
I can't.
This is the right answer. Oh, no, this is wrong because these 2 states are sharing the same color, right? But finding the correct combination, that is what is difficult. Are you familiar with the traveling salesman problem, Caarn? No, because you're not born in the 1960s. However, back in the day when salesmen went door to door and town to town, there was a problem that was developed, which is given a random amount or a certain number of cities on a map, how do you find the most ideal path for this salesman to visit each city once and only once and return to the starting point in the shortest amount of travel possible? This was a real problem that real people faced, right? Once you have a solution, easy to verify, but it's difficult to come up with the correct answer. Another one that you might be more familiar with is certain types of encryption.
Oh, no.
Right? Now this is where it gets, certain types of encryption depend on finding 2 large prime numbers and multiplying them with each other and then getting a much larger number, right? It's easy to see if the answer is correct, but it's very difficult to go the other way. It's very difficult to start at the answer and then go back and find out what those numbers were. So really the going backwards part, that's the NP problem, right? But once you have 2 numbers, it's easy to check if those are the correct numbers. All of these are NP problems, and quantum computers are really good at solving those specific kinds of problems. Quantum computers do this by using things called quantum algorithms and quantum operations. There's a whole bunch of them. We just looked at some. You're going to see these names through the talk. But there's, for example, there's Grover's algorithm, there's Shor's, there's Bernstein-Vazirani, there's the Hadamard transformation. Like I said, you're going to hear these names. We're going to talk about some in more detail than others. But these are just operations that can be performed on these qubits to be able to get some sort of result, right? Shor's algorithm in particular that we're not going to talk about is really good for breaking certain kinds of encryption. It's really good for finding prime numbers that give you another value, right? But another one that is not as good, but it could still be used, at least experimentally, and that's the one I want to talk about because it was the one I kind of understood, is Grover's algorithm. So this Grover's algorithm would be quite useful for breaking those specific kinds of encryption. Now, Caarn, it's your time to shine. Do you know who Grover is?
The pervy Sesame Street.
It is a
Grover.
pervy Sesame Street guy. He is not the one who came up with the algorithm, however.
Oh, thank God. Is this Kumar?
This is Kumar.
My God.
So this Grover is not coming for your nudes. He's not looking to break encryption so he can find your nudes. I don't want to look at your nudes. So I don't think Grover does either. Again, it's not this Grover, but it is weird that he was wearing a hat and a cape, no pants. Around children, right? But no, different Grover. Like Caarn said, it's Love Kumar Grover, who is a computer scientist.
What a name.
He came up with something called the Grover search algorithm. And this algorithm is good for searching through unstructured data. Now, I went and did some research on how it looks. And it looks like this. It's actually quite simple if you look at it. You initialize the system, make sure there's superposition. And then really the ket of S equals 1 divided by the square root of the number of steps. Listen, trust me, it works like this. I don't understand it. I'm not a math major. Is anyone here a math major? Oh, shit.
Get out.
Please leave, because you will be offended by the end of this talk. But most everyone else isn't, so that's good. I think it's easier to understand it if we kind of see it in action, right? Before we get into that, though, there's a concept that I haven't talked about yet, which is quite fundamental to a lot of quantum computing, and it's the concept of the oracle. Are you familiar with the oracle?
Like the one from the Matrix?
Like the one from the Matrix, kind of. If you remember the one from the Matrix, Neo and all of them would go ask for answers, and she'd always give these like vague-ass answers. It's like, I think she meant this, but maybe she meant something else. It's kind of like that with the quantum oracles. The quantum oracle gives answers, but these answers, they are useful, but they're only useful to a certain degree, right? Think of the oracle as this mysterious black box, and it's called a black box. That is the oracle from the Matrix. She also happens to be a person of color. I'm a person of color, he's a person of color, so we meant no disrespect. That's the computer science term, right? It's a black box because you don't know what's happening inside of it. So no one take offense, please. If you've sat here this long, you haven't taken offense already, so I'm not going to start now. But an oracle is this black box that you give it an input, and it will tell you yes or no, right? You don't know what is happening inside of it, but basically, you give it a value, and in classical computing, it would return maybe 1 for true, 0 for false, right? Think of this problem. Say you have a list of values, 1, 2, 3, 4, 5, 6, up to n to the minus 1, right? And say that you are searching for one of these values. Let's say, for example, the number 5, right? If we had this black box in classical computing, when we gave it number 5 as an input, it would tell us, yes, that's the one you're looking for, right? Any other number, it would say, no, sorry, try again. Don't get too caught up on this, but you could say that this is what the black box looks like on the inside. It could have a super simple function that says if x equals 5, give me true, otherwise give me false, right? Don't think too much about that because quantum black box works differently, so you're going to say like, wait, but this makes no sense. We'll talk about that. But this is how this works in quantum. So I'm going to talk about both the black box and the algorithm at the same time. In Grover's algorithm, you take this list of values. First off, those characters you see around the value, the line and the greater than sign, that's called a ket. So a ket is put around a value that is worked on by a quantum computer. So if you see something that has a ket around it, it means that quantum computer is working on this, right? The opening slide had that cup with the kid. I was in love with it. So the black box in quantum, remember, remember the classical one, you could give it one value at a time, right? You can't just throw all the values at it. The black box in quantum, you can give it all the values at the same time if you have the capacity, if your quantum computer has enough qubits to work on all of them at the same time. You give it all the values at the same time, but here's already where it starts to get different. These values, before you give them to the black box for the first time, they are all given a probability. What does that mean? It means that when you start searching through them, the quantum computer says the first thing is I'm going to give all of them the same weight. Remember, these are represented by qubits. And remember how I said that when you look at a qubit, it's kind of like flattening that coin. What's going to come up? Right now, if I were to ask it what is the answer, it will give me any answer because the probability of all of them is the same. But I give this to my black box. Black box says, here's one value. It doesn't say that. Black box looks at all the values, sees one that satisfies the rules of whatever black boxiness is going on, and takes the probability and gives it a minus sign. That's all it does.
Revolutionary.
Crazy, right? Already mind-blowing. What is the use of this? You might think this is completely useless, but it's not useless. There's a second step now to Grover's algorithm where we take this list, we perform a vector transformation. I'll talk about what that is in a second. And now, the probability of the correct value has increased while all the other ones have decreased. Already, you're like, whoa, how did this happen? We'll get to it. I think it's even easier to understand this if we look at a diagram. This is a very, very simple 2D representation of what is going on inside of a qubit. But think of a qubit as a sphere, because actually I think that's, if you could look at the qubit, I think that's what it looks like. It looks like a sphere. And any point on that sphere, you could say the top of the sphere, if it's like planet Earth. You got the North Pole, the South Pole, you could say that's the 1 and the 0. But then there's everything in between that is neither full 1 nor full 0, right? The qubit is basically representing all of those, that full 1, the full 0, and everything in between at the same time. And remember, when we start, each one of those values is given an equal probability of being what comes up when we ask the qubit, what do you got for me? So think of as all those potential values as the horizontal line on this one here, right? And the blue line is all of our potential values, all the wrong ones plus the correct one, with their probability evened out. So you can see that this blue line is almost the wrong answers, all the wrong answers, but it's not because it also contains a little bit of the correct answer. The yellow arrow is the yellow, yeah, let's call it arrow, is the correct answer, right? So the blue line is the average of all the wrong answers plus a tiny bit of the correct answer. But right now you can see the probability. If I were to ask this qubit right now, what is my answer? The probability is that it's going to come much closer to here than it is to up there, right? But now remember, we take that first step where we ask the black box. Black box look at these values and says, yeah, I'm going to give you a minus on the probability on this one.
The Oracle says this one.
Oracle says jump, and you can't ask why, you just got to jump. So what happens next is that you see now my probability has gone now on the negative. This is that negative transformation we did to it. And you might say, like, okay, now we're even further away from the correct answer, but we're going to get there. Remember the vector transformation we talked about as a next step. This vector transformation is really just flipping the axis over the original line that we had, the original average of all of the probabilities. Trust me, bro, this is it is complex math, and again, this is just a 2D representation. But what happens here, once we flip it, you see, now we're getting closer. Now we're actually a little bit closer to the correct answer. We're still not there. If we ask it right now, it's still probably not going to give us the right answer, but we are getting closer. So when you rinse and repeat this a bunch of times, here's an animation showing it. You see, we do it the first time, we're in the negative. We flip it, we're getting closer. We get the negative again, and we flip it again. And we keep doing this over and over. And you can see it's getting closer and closer to the correct answer until you are close enough that you can say, okay, let's find out if we have the correct answer. So, I know you have a lot of questions. And I know the first thing you're thinking, doesn't the oracle know the answer? Why are we doing all this when we could just say, okay, let's look at that list of probabilities, which one got the minus? That's the correct answer, right? But that's the thing, the oracle does not know the answer, first of all. Again, remember, the oracle knows what a correct answer looks like. It knows the rules of Sudoku, but it doesn't necessarily have already a correct solution in place. It's not doing the if x equals 5. It's just saying, if this input satisfies all of these rules, all of these conditions, then that's maybe the correct answer. So that's the first thing to remember, right? So when we give it our list of values, it's going to say, yeah, this one seems legit. Looks like that might be the one.
Checks out.
Another thing, remember the superposition. When this coin is spinning, Glenn and I, we got money on the table. We're waiting to see if it's heads or tails. We cannot say, okay, now it's heads, I win. You have to wait until it stops or until you stop it. We call that collapsing a qubit. Once we stop that coin does not start spinning again. We can't stop it, look at it, and then it just whoop starts spinning again. Once it's stopped, it is stopped. It has ended. And it's the same with the qubits. They are in all of these states at once, and we're performing these checks on all the states at once, but we cannot look at what is called the state vector, the one keeping track of all the probabilities. That is just some quantum stuff that we just cannot do. The qubit knows, but we don't know. It's like looking inside of planet Earth. We can't really do that. We can just see what's on the surface. And once we are ready to ask our qubit, then we have to collapse it. We're basically flattening this qubit and see if what comes up is a 1 or is a 0. Trust me, bro. If you collapse this qubit too early, you're going to get randomness. And you're actually going to get, it's pretty cool, you're going to get true randomness. It's not like, none of that like lower shelf pseudo-randomness from classical computers. This is true randomness. We're not going to talk about that, but that has other uses, right, within computing using this true randomness. But remember how like that arrow was so close to all the wrong answers in the probability chart? So chances are you're going to get the wrong answer. If you do it too late, you're also going to get randomness. Because remember how it was getting closer and closer to the correct answer? If you keep on going, then it starts going away from the correct answer. It goes past it and the other way. However, if you collapse it after exactly pi divided by 4 times the square root of the amount of values, you have a very high chance of getting the correct answer. Now notice the very high chance. There is a tiny probability that you still will get the wrong answer because it's never really 100%. But very high chance. And that's why quantum computers, they will do this a bunch of times also and also average the results. So if you get one bad qubit that didn't give you the right answer, all the other ones will give you the right answer. You end up with a valid answer, right? Trust me, bro. So is it really that fast? Like, we still have to do a bunch of iterations on it, right? So it's not instantaneous like I was promised. But how fast is it really? Well, if we're doing it with classical computing, if we were going to search through that list, I have the answer here already, but the amount of steps you would need to take to work through that list, putting each value in the black box and so on to find the correct value, is about half the total amount of values, right? Because it might be the first one, it might be the last one, but if you do it over a bunch of times, it averages out to about half of the amount of values, right? Anyone want to take a guess at, well, okay, so before I say that, so that means that for 1 million steps, for example, 1 million values, we're looking at about 500,000 steps. Anyone want to shout out what you think quantum is? How fast quantum can do it? You don't need to shout out an equation if you don't want, but
200,000.
Do we have more?
Oh, 300.
We have less.
150.
Thank you, Caarn. Quantum computing, it actually does it at a quadratic. It's a quadratic gain. So it takes about the square root of the total amount of steps. No, the total amount of values. That's the amount of steps you're going to need on average to find your answer. So we are going from 500,000 to 1,000 with a somewhat unstructured list of 1 million values. But now this is not what I was promised, Caarn. I was told that quantum computing was instantaneous, was super fast. I was ready to crack all these cryptocoin wallets.
Newts.
And this seems like it's not so fast. What if I wanted to be much faster? What if I wanted to be done in one step, one repetition? I'm hearing you got a demo.
I got a demo.
This is a different algorithm. Now let me ask you, Connor. Is this a quantum computer? How are you going to run a demo here?
Well, for the low price of $9.99. So you guys thought I was just here to look pretty and make jokes.
You did look pretty, though.
Thank you.
My turn.
All right. Time to speed run.
I have a joke.
We'll find out. All right. Let's figure out first.
Is my fat head in the way, or people see the screen? Yeah, all right.
To entire screen. Start mirroring. Let's see. Oh, look at that. First try. All right. So what we'd
People
like.
in the back see it? Yeah?
Do we,
All right, let's
thumbs
see,
up? Yeah?
yeah.
All right.
It's
I try to
quantum.
make
They
it
can
big.
both see it and not see it.
Okay. So what I did here,
That was my one joke. It's not good. Go on.
I've got a few helper functions here, but we're going to try to speed run this algo. And then leave some time for some overall thoughts and conclusions. But to Eugene's point, there are some instances where we can maybe get constant runs.
Now, what kind of data would I need to have for this?
Oh, I'm glad
Can I
you
do it
asked.
on unstructured data?
No, you must have structured data. And I think what we're going to end up with here is a very certain set of structured data in a black box oracle. So for our particular go at this, we're going to simulate turning on light switches. So imagine you have 20-odd light switches. They can control a light, and we're going to form this into a sort of bit string, if you will. And we need to check if the switch at a certain index turns on the light. Classical approach to this would be to go one by one. Flip the switch, see if the light turns on, record it. With quantum, however, we can use all of our qubits and simultaneously get the answer.
In how many steps, Caarn?
In one step.
Nah, you're kidding me now.
Dude, are you kidding me? Are you
$9.99, you say?
$9.99. So, I'm not sponsored by Microsoft, but I am using Q#. If there's anyone who works at Microsoft in the audience and they want to sponsor me, then I'll do this on an actual quantum computer. I mean us.
Thank you.
Okay, without further ado, let's get to typing. All right, so first, let's actually take a pause. So just down here, we've got some helper functions to create our sort of array and format it according to, one, we just want to make it look pretty. And then in our main function, we're actually going to sort of set things up and run. So I guess first sort of row, some numbers between 0 and 19, ideally. 17. All right. Anything else? 18? Anyone else? 9. All right. Let's put it out of order just to see if we can break it.
Dang.
Okay. These are our light switches at those particular switch intervals out of the 20. Okay? Remember that. We'll come back to it. So going back to actually write it, we're going to go ahead and first get the length of our secret. And I'm typing on a Norwegian keyboard, so bear with me. And then we need to get some qubits, get these bits. How many do we need? Well, we have 20 light switches, but we actually need one more, and I'll explain why here in a second. I feel like we should have some background music or something.
Some elevator music.
Yeah. So first we need our input qubits. So we'll take a subset of what we already have. And for those, I want the first 19 or 20. And then
I wish I knew what he was doing so I could maybe point out areas if I saw any, but I have no idea what any of this is. So this was his part of the talk, as you can tell.
we are off to the races here, folks. Super interesting stuff here. All right, setup complete. Thanks for bearing with me. All right, so you may notice ancilla. What the heck is ancilla? I don't know why they call it that, to be honest. It's just something that we're going to track the state and use as a comparator later on to influence or sort of do the entanglement with our qubits. But,
Trust me, bro.
Yeah, this is a trust me, bro. Further trust me, bro, we need to set it up and set the state. And it's not just a normal state, because why would we do that? We need to actually perform some operations. So first is a Pauli gate or X gate on the ancilla. Oh, gosh. Then a Hadamard gate. Now this one we kind of do already know, we have talked about. So we use Hadamard gates to put bits into superposition.
I didn't name it though. Which one's that? That's the one that averages out all the values,
Mm.
right? Correct.
Mm-hmm.
So remember the very, very first step that you only do once? That's a Hadamard gate.
Now, if I can spell apply, now we want to add or put all of our bits, input bits, into superposition. So we're like, okay, we've got our comparator, we have our bits in superposition, now what? Well, it's black box Oracle time. And for this, actually, I kind of want to switch to a slide here. Let's see if we can make this work more fast. This is the formula that we're going to go ahead and mock up here. Extremely simple. So we're not. We're going to kind of fake it because doing this implementation live would be masochistic. Okay, so for index, yeah, looking all familiar, right? Not too complex. So we're gonna iterate through and we're gonna check if the secret at that index is true. And then now we're going to apply a C0, which is kind of like the classical equivalent of an XOR gate or operation. So we're going to do that to our input qubits at that index. And then we're going to pass in the ancilla as well. And this is what's going to influence the bits. All right, so we've touched the bits now. What do we want to do? We need to flip them again, right?
You're not allowed to do that.
They're my bits. I can do what I want. So, once again, we are going to apply a Hadamard. And this is the sort of step where we are sort of inverting over the axis. So, okay, now we've got the bits where we want them, right? We need to measure them. So this is where we're going to collapse everything. First, we'll go ahead and create a mutable array.
That's where we look at the qubit, right? There's no more qubiting after that.
No, this
Correct.
is the end of the qubiting.
Yeah.
Yeah. Okay. Oh, nearly there. Nope, wrong one. There we go. It's the So did I nail it? And similarly, we're going to go through here. All right, now is the fun bit. Let R equal measurement. This is, we're going to collapse it. Now, I know what you're thinking. It looks pretty simple.
I was not thinking that at all.
Well, some of you may be thinking it was simple.
Math major.
He left, or she. And then, yeah. So now that we've got the result we've measured, we're going to set that into our results. Plus equals, there we go. And now, the moment I've been waiting for. After cleanup, which we're going to do, we're going to reset all. Not that we're going to do anything right now with them, but, good practice. Why not?
You got to keep your qubits clean.
And we're going to return our result. Speed run done. Okay, now, if we run this, and I did it right, we should see the switches. Who's ready?
Let's go.
Let's go. Now,
I enjoyed that. I have no idea what happened, but I enjoyed it.
underwhelming? Maybe. So there are lights, so I can't really see everyone, but now that we've gone through the demo, can I get a show of hands? Who's skeptical about all this shit? No one's skeptical? Ah, there we got some. Yeah, okay. Less than expected.
Let me cover the numbers real quick.
Maybe we did a good job.
Yeah.
No. So it was the index out of 20. Should have clarified.
Sure. Yeah. Trust us,
Trust
bro.
me, bro. It worked.
All right. I forgot how to reflip
there you go.
this. Which one is it?
Choose content.
Choose content. I know computers. There we go.
Yeah. Extend.
Extend, right?
Extend.
Did
There
that
we go.
extend? That did extend. All right. Let me get back to. I'm way overextended.
Been that way the whole talk.
All right. Let's see. Does this still work? Still works. So, Caarn, did we learn anything? Like quantum, both yes and no, right?
Yeah.
It's complicated. Caarn, is it faster than classical computing? I presented this part, so I know the answer. Is it faster? Sometimes is the correct answer. Because, yes, it is for certain things, like that experiment with the light switches just now. Also, not really for several reasons. First of all, if you take each individual computing step by itself, classical computers are still much faster than quantum computers at just performing one computing step. Also, we just don't have that much capacity yet. I tried to find out what the largest quantum computer is right now. Some months ago, it looked like the record was 1,100 qubits in a computer. Someone recently managed to cram 6,000 in one, but I think it was just like a one-off, very experimental. This is not stuff you can go and run your workloads on. But also, too, remember, these qubits cannot just exist freely. They need to be entangled so that you can do more than just find a 1 or a 0. Because one qubit, at the end of the day, will only give you 1 or a 0. You have to have multiple of them so you can work on larger and larger amount of values. So the max entangled qubits I could find is 50. Seems like someone managed to get 50 of them entangled. So this still gives you a very large number, but we're not really there yet. So you cannot do anything super complex. You're not going to be able to go crack your cousin's crypto wallet tomorrow. It's just not a thing you can do just yet. Because remember, 2 to the max number of entangled qubits gives you the amount of bits you can get out of the reading. Next question. So this kind of relates. Will quantum computers replace classical computers, Caarn?
Not a chance.
Not a chance.
No.
They are very, very, very specialized computers for a very specific type of problem. They're going to be great at those kinds of problems. Finding new materials, finding how certain things happen within DNA, finding how proteins bind. Those kind of things where you have one answer in a huge haystack of potential answers, they're going to be great at that. But you're not going to be running Crysis on them. You're not going to be running your video games on them, right? So the answer, I think simply we can say no. And it's kind of like GPUs are super powerful, But no one would say like, well, I'm getting rid of my CPU, I'm just going to put a GPU in there instead, right? GPUs are very powerful at doing one specific type of computing. But they're not going to, quantum is not going to replace classical the same way GPUs are not going to replace CPUs. Are my nudes safe? Caarn, I need to know, I must know. Because I saw this headline, and I've seen a bunch of headlines like this. China breaks RSA encryption with a quantum computer, threatening global data security. Global data security includes my nudes. Well, maybe, maybe not the security part. These are sensationalist. Once you read the article, the RSA encryption they broke, I think it had like, I can't remember if it was like 20 bits or something. No one's doing RSA to 20 bits. You know, actually, most people are not even doing RSA to begin with anymore. So, not really. Maybe one day in the future, just delete your nudes. Just don't have them there. You're just asking for trouble. Oh, pick really, pick flattering ones. That might be a good point. And really, the question that everyone came here to find out: can it run Doom? Let's see hands for no.
Yes.
Let's see hands for yes. Well, like everything quantum, the answer is somewhere in the middle, right? You can't run Doom on a quantum computer. There is a port. It does work. It looks like this. However, the amount of qubits that you would need to run this is 72,376. Remember, 1,000 qubits is the limit, so you can't run it on your laptop on a quantum emulator. You can't run it on a real quantum computer just yet. Should you drop everything and become a quantum engineer, Caarn?
No.
Correct.
Maybe.
Maybe.
Probably not.
Maybe if you love the math. Maybe if you like are really interested in that. But otherwise, it's not going to destroy anything. It's not going to change how we do everything. Trust us. Famous last words, right? You want to learn more, you can find the slides on that URL at the top. So then you can just go in. You don't have to write down these links. But take a quick picture because we are out of time. We strategically planned it so that there could be no questions because we will not know the answers. That's
Mission
us.
accomplished.
Mission accomplished.